All right, the last set of notes for the equilibrium subunit will discuss the Chatelier's principle. This is a little more conceptual than mathematical, but we're talking about what happens when you take a system that was at equilibrium and then do something to change it. What Le Chatelier's principle tells us is that if you have a system at equilibrium that experiences an external stress, in other words, if you do something to knock it out of equilibrium, the system's going to respond in a way to relieve that stress and essentially undo what you just did so that it can get back to equilibrium. So if you put a stress on something, put a stress on the reaction is going to do something to get rid of that stress to reestablish the equilibrium that it had before. So what's actually happening is that when you change the state of the reaction, when you change the state of the reaction away from equilibrium, you're no longer at that K value. You're no longer at that value of the equilibrium constant where you have that correct or proper ratio of products and reactants. So we say that we temporarily establish a Q value. That Q stands for reaction quotient. You calculate it the same way. You calculate it the same way as you would K, products over reactants raised to their coefficients. But the whole idea is that Q is some state where you are, whereas K is the state that you want to get to. Now, if you get to a state, you get to a position, you get to a situation where Q equals K, then, oh, congratulations, you're at equilibrium. So let's talk a couple of ways that you can change the conditions of that reaction. The first way we're going to talk about is changing the concentrations of your reactants and or your products. So if you have this reaction, H2 plus I2 gives you 2HI. If you're initially at equilibrium, right, we're talking about if you're in this general area over here on this graph, if you're at equilibrium where Q equals K, then your concentrations of the reactants and products are constant but not necessarily equal. Now all of a sudden, let's say if you add more H2 gas, so then all of a sudden your H2 concentration goes up. What you did was you're no longer at K, but now if you add H2, you're at a Q value where you still have your HI on the top and your H2 on the bottom and your I2 on the bottom. But now if you added more of that H2, now all of a sudden your denominator got bigger, so we can say that the Q that you just established is less than K. So if Q is less than K, in other words, not equal to K, then that means you're not at equilibrium anymore. So if you're not at equilibrium anymore, the reaction is going to respond in a way to get back to equilibrium, to undo what you just did. So if you added H2, in this case, H2 is a reactant. So if you added a reactant, the reaction is going to shift to try to get rid of that reactant. So what's going to happen is that the reaction is going to shift to the right, right? It's going to shift the right to temporarily favor the forward reaction. It's going to favor the forward reaction to consume the excess reactant that was added. Right, you placed a stress on the left side, so the reaction is going to run away from it and shift away from that stress to try to relieve it. You added reactant, use up that reactant to try to get yourself back to equilibrium. So as you go to the right, you can notice how the H2 concentration starts to go down, but what happens along with it? The I2 also goes down because you're also consuming the other reactant, but then the product, the HI, starts to go up. So you use up your reactants, you make more product until Q equals K again, and you're back at equilibrium. So it's going to shift until Q gets back to equaling K, and then all of a sudden, hey, congratulations, you're back at equilibrium, but you'll notice these concentrations are different from these concentrations. But the ratio, when you plug them into the K expression, are going to come out to the same value. So the actual concentrations will be different, but their ratio will come out to be the same. So now let's look at what happens if you do a bunch of other different things. So if you add I2, right, you're adding reactant. So if you add reactant, the reaction has to shift right to consume it. To consume the added I2. Now, if you add more HI, on the other hand, now you're adding something to the right. You're adding product. If you add product, then we have to shift to the left to consume the HI. But now you can change the concentration by adding, or you can change it by subtracting. So if you remove some HI, you can think of it like you just created a hole. You just created a deficit on one side of the reaction. If you create that deficit, the reaction is going to shift toward it to try to refill the hole that you just created. So in this case, you're going to shift to the right to replenish the lost product. Now, another way you can disturb a reaction, this case is specific to gases only, is by changing the volume or the pressure of the container. If you make the container smaller, if you decrease the volume, thereby increasing the pressure, remember, pressure and volume are inversely proportional. If you decrease the volume, increase the pressure, the reaction is going to try to shift toward a way that can make it less pressure. You want to lower the pressure to try to relieve that increase that you just created. The way you do that is by shifting toward fewer gas molecules, right? Less gas means you're going to have a lower pressure. So if you've got this reaction where you've got N2 plus 3H2 goes to 2NH3, if you increase the pressure, you want to make it so that you go in a direction where there's going to be less gas left in that container to try to relieve that pressure. So in this case, if you increase the pressure, it's going to shift to the right, because over here we've got 2 moles of gas, whereas over here we've got 4 moles of gas. Now, if you increase the volume or decrease the pressure, in other words, if you create more space within that container, the reaction is going to shift toward the side with more moles of gas to try to fill up that extra space that you just created. Now, if you've got a situation where you've got the same amount of gas on both sides, then there's really no preference to go one way or the other. So in this case, it's not going to shift the equilibrium at all. That only changes the equilibrium. Changing volume or pressure only changes the equilibrium if you've got a different number of gas molecules, different amounts of molecules of gas on the left side versus on the right side. Now, the last way we're going to talk about affecting the equilibrium is by changing the temperature. Now, the important thing here is that what's actually happening is that when you change the temperature of a reaction, the actual value of the K changes. You're establishing a new K value, right? Any K that I give you is only valid for a specific temperature. If you raise the temperature or lower the temperature, you're going to have a different value for K. So we're not actually establishing Q, right? There's no Q value involved when you're changing the temperature. but you're actually shifting the true value of the equilibrium constant. A little shortcut you can use is to think of the heat as either a reactant or a product. If you have an endothermic reaction, in other words, heat's being absorbed, you can think of heat as being a reactant, or in other words, being on the left side of the reaction. If you've got an exothermic reaction where heat is being released, then it's going to be coming out of the reaction like the products. Now, if you take this example of N2O4 and NO2, this has a positive value for delta H, so it's an endothermic reaction. That's why heat is a reactant on the left side of this reaction. When the system gets hotter, in other words, when T increases, then the reaction shifts to the right, and what's actually happening is this is going to consume the excess heat that you added, right? You added a reactant, you shift towards the products. Now, when you make the system colder, when the temperature goes down, you can think of this like establishing a hole where the heat was. So whenever you establish a deficit, whenever you establish a deficiency in that reaction, the reaction's going to shift in a way to refill the hole that you just made. So the reaction will shift left to replenish the lost heat. Right, so if you have an endothermic reaction, think of heat as a reactant. If you have an exothermic reaction, think of heat as a product, and then raise or lower the temperature and think about it as adding or removing heat. Now again, this is just a shortcut because it's not really the case where heat is a reactant or a product. It's not actually participating in the reaction. But we're talking about how to shift the value of K one way or the other depending on what the value of the delta H is. Now the last way we talk about changing a reaction is by adding a catalyst. But adding a catalyst affects the kinetics. It doesn't actually disturb the equilibrium, because what actually happens is that both the forward and reverse reactions get faster. Right? It increases the rate of both the forward and reverse reactions by the same factor. So it doesn't change where the equilibrium is. What winds up happening, the only difference is that you reach the equilibrium faster than you would have originally, right? Because both activation energies go down, both reactions get faster, so you get to an equilibrium state faster, but it doesn't shift to the left or to the right. So just remember, if you create a stress on a reaction, if you do something to disturb an equilibrium, the reaction will respond in a way to undo what you just did to get back to the equilibrium.